I'm Professor Brad Fulton, and welcome to my Stats podcast. This is an edited audio recording of my course. Each lecture is its own episode, and there's a total of 24 lectures. This course provides an introduction to the quantitative methods social scientists and data analysts use to collect and evaluate empirical data about society. Through this course, you will learn to gather, describe, and analyze data with an emphasis on the application and interpretation of these methods. This course will also help you to be a more informed and critical reader of academic research, public opinion polling, and advertisement claims that present statistical evidence. Although some of the current events I reference might be dated, the content is timeless. I hope you enjoy this lecture, and if you have any questions, you can email me at bradrfulton@gmail.com. Hi, my name is Professor Fulton. If you like this podcast, you'll love the book I use for the course. It's titled Statistics, Unlocking the Power of Data. This book uses a highly intuitive approach to help students visualize statistical concepts, which accelerates understanding. I've reviewed dozens of textbooks, and Unlocking the Power of Data is hands down the best one out there, mainly because of its unique intuitive approach and straightforward explanations. You can find a link to the textbook in the show notes, and if you use the promo code BLOCK5, you'll get a 10% discount. That came up when we were talking about correlations for part 2. So with correlations, there's 3 things that we can find from just an R value of 0.66. There's 3 things that we can pull from that. And the first one that we want to do is we want to ask, is this correlation statistically different from 0? You could have R, or the correlation, equal to like 0.2, but if you looked at the confidence interval for that correlation, it could overlap with 0. And so then you could say this correlation that we found could have happened by random chance, and there'd be no correlation between the 2 variables. Just because you get a correlation value doesn't necessarily mean that there's a correlation. So the first question you need to ask is this statistically different from 0? And that's where you look at the confidence interval of the correlation, and that's this equation right here. The next question, after you've determined that it is statistically different from 0, then you're going to look at, well, what's the direction of the correlation? And that's just basically, is it positive or negative? And then the third one is looking at the magnitude of the correlation. So all 3 of those are different aspects of correlation. So you can't really just say, oh, X is correlated with Y. You need to say the direction of the correlation and then the magnitude of the correlation. And so even with the example of the respondent's education level and the spouse's education level, what I'm looking for in those is that the respondent's education level is correlated with their spouse's education level, positively correlated. And the thing that I thought was interesting, and you guys picked up on this, was that there's a strong correlation between the respondent and their spouse. There's a correlation between the respondent and their parents' education, and then both their parents have a strong correlation. But what I thought was interesting in that is that if you compare all the correlations, the mother and father, the correlation between their education levels is higher than the correlation between the respondent and their spouse. And so what I saw in that was a generation ago, people's education levels were more correlated than they are today between partners or whatever. But it's beginning to interpret, and that's what, with the final research project, that's what you'll need to do. It isn't just sort of coming out with, okay, yes, these are correlated, but it's interpreting what you're seeing and it's giving a sociological explanation for the numbers that are coming up. That was something that came up with correlations. So for today, like I said, for 4 days straight, we're just going to be looking at inference for categorical and quantitative variables, and it's going to be repeating itself, taking stuff that we've learned in the first section of the course and then applying it through a different means to make inferences about the population parameter. And so this is the second part with categorical variables, where we're looking at differences in proportions. So the previous lecture was just looking at a single proportion. So now this is going to take it one step up to look at differences in proportions. And so that's notated by P1 minus P2. And this is kind of a tricky thing, a little mind bender type thing when we're talking about proportions, and it's important to get clear in your head how you differentiate between when you're talking about just one proportion and when you're talking about two proportions. Because you'll get a question, you'll be like, okay, is this just one proportion or is this two different proportions that we're looking at? So with one proportion, there's only one categorical variable. You're looking at, I think some of the examples were wins versus losses of games. And so the categorical variable is just one categorical variable of the number of wins in a season. And it can be confusing because if you have the proportion of wins, which is like, let's say 0.60, you also know the proportion of losses, which is 0.40. But you're still just talking about one proportion. There's only one variable that you're looking at. And then with two proportions, there's two separate categorical variables. And this is examples where we did like race and gender, or categories for income. It could be gender and income or something. So you're wanting to look at two different categorical variables and the relationships that they have with each other. Here's an example. A study sampled 356 college students to estimate whether a greater proportion of college students are female or male. Is this a one proportion or a two proportion, Brittany?
One proportion.
One. Okay, let's see. Hey, you're right. It's one categorical variable that we're looking at, which is gender of students. Basically framed in this way, are you female or male? And then the sample or the test statistic for this would be p hat f, the sample proportion of female students 0.47, and then you can also know the sample proportion of male students is just 1 minus p hat. So that's how you look at a one proportion. And then here's an inference for two proportions, almost set up the same way. A study sampled 356 college students to estimate whether females are less likely than males to be engineering majors. What are the two categorical variables that they're looking at in this? Major, yeah. So gender and major. And that's important to kind of know what are we measuring, and then you have specific values within that. So are you a female or male, and are you an engineering major or not? And then the way that you would look at the test statistic for this would be p hat fe, which is the proportion of female students who are engineers, and then the way you could find the opposite would be you take the total proportion of female students minus the proportion of female students who are engineers, and then you could find the sample proportion of female students who are non-engineers. And I even think in the first exam, this kind of threw off some people of like, what proportions am I looking at? If you set up the problem incorrectly, it's going to make the rest of the solutions go in the wrong direction because you're measuring the wrong proportions. So as we talk about two proportions, it's just important to know which subcategories are we looking at. And then the same can be set up for male engineers. Visually, this is how you would do it. You'd say, here's the proportion, and so you can kind of see you're working with two proportions. What we talked about in the previous lecture was how do you measure standard error for proportions, and so for a single proportion, we had this formula. And so fortunately, for two proportions, or the difference in proportions, it's very similar, where you have, here's your test statistic, which is p hat 1 minus p hat 2, so that's with the engineering and majors. With gender and majors, it'd be the proportion of female engineers minus the proportion of male engineers. You can kind of see some similarities with the two formulas. It's basically taking the standard error of this first sample proportion and then adding to it the standard error for the second sample proportion. In standard error is how much error is there in your point estimate. That's sort of another way of thinking of standard error, is how much error is surrounding your point estimate. If you now have two variables that you're working with, you need to account for both errors in those. So that's why you would add it. This might be a little bit confusing. N1 is the sample size for group 1, and N2 is the sample size for group 2. So almost think about, you have your total sample, and then when you do this type of test, you divide your sample up into two groups based on what you're looking at. With this one, it's looking at females versus males, so you kind of have a new N. You have N1, which is all your females, and N2, which is all of your males. So N1 plus N2 will add up to the total N. In the last lecture, we said we don't know the population parameter, the population proportion in most cases, and so we can estimate it using the sample proportion And so that's what we did here, convert this to an equation where we have known values. And so in the same way, we convert this equation to this by substituting P1 with P1 hat and P2 with P2 hat. So these are all our sample proportions from our study. Takes what we've already learned, but then expands it to when you're looking at two proportions or a difference in proportions. Like we've done before, the way we set it up is we're going to be looking at confidence intervals and hypothesis testing. So you're going to see this repeated over and over again. How do you calculate confidence intervals and how do you calculate hypothesis tests? This should be a familiar formula where you want to know the X% confidence interval. It equals the sample statistic plus or minus Z star times the standard error. What would be the sample statistic when we're talking about differences in proportions? What would be the thing that would go in right here? So that's the sample statistic for when we're doing differences in proportions. And so this is the general formula, and then this is the specific formula when we're talking about differences in proportions. And it's basically substituting the things that we just looked at. So what Brittany said, you put in your sample statistic, you have your Z star, and then this is the standard error equation that we looked at. To remind you, Z star, it's the location on the standard normal distribution, and its value is determined by the confidence level that is selected. So the way you calculate Z star is basically you have that normal distribution, and so if you want a 90% confidence interval or whatever it is, you find out what's the upper bound of that confidence interval, and the value on the x-axis is going to give you the Z star. Z star will always change depending on what your confidence level is. So for a specific example, we'll do gender and engineering. So a study sampled 356 college students to estimate whether female students are less likely than male students to be engineering majors. So this is an example of, in a sense, a research question that you'd be faced with, and you're like, okay, how do we go about answering this? Well, we need our data. And so from the data, we see that 20% of the 167 female students are engineering majors, and 36% of the 189 male students are engineering majors. So just by looking at this, can't we just answer the question? So the question is, are female students less likely than male students to be engineering majors? Why can't we just answer the question right here? Brittany?
You don't know if it's like outside the range of what could occur on normal change.
So it could be that with the null hypothesis, that there is no difference between female and male engineering students, and this sample could have just occurred by random chance, this configuration. Even though there's only 20%, the good thing when we're dealing with proportions, it doesn't matter that these numbers differ because we're looking at the proportion who are engineering majors. And so it's okay if you have even, say, 300 females and only 100 males. When you're looking at proportions, it levels the playing field as far as the number of people that you're looking at. So give a 90% confidence interval for the difference in proportions. If we have a difference in proportions, a point estimate, we want to know what's the confidence interval for that point estimate. This is putting it in what's called a two-way table, just taking the data and putting it into a more concrete form. And one of the tests when you're looking at proportions is there at least 10 observations within each cell or category. You know, if we set this up and it turns out there's only 3 women who are engineers, we couldn't use the formula because there's not enough observations or not enough people in one of the cells, and so it throws off the equation, or some of the assumptions we make won't hold. Since there is at least 10 in each category, we can move through this so then we notate the 90% confidence interval, and here's the general equation that we use, and I'll show you how we get the 1.645. Can someone explain to me how I would do that on StatKey? What would I pull up on here if I want to find out what Z star is for a 90% confidence interval? What distribution are we looking at? Okay, normal distribution. Along the bottom row here is Z values, and so we want to know what the Z value is for 90% confidence interval. The range of values that are in the middle 90%, how would we? Okay, so two-tail. These numbers up here tell you the proportion of values under the curve for that area. So we want to know the middle 90%. So you can go right here. Right now it's giving us the middle 95%. And click on that and say we want the middle 90%. And then we can just go down to where the upper bound is, and that gives us what the z star is, 1.645. And you'll need to be able to do this for all the assignments, because just by saying 90% confidence interval gives you enough information to be able to look at this curve and calculate what the z star should be. The p hat 1 minus p hat 2 pulls in the proportions from this table. And again, doing the math is critical for this, making sure you have your proportions right. The same is plugging in the appropriate number. So what is 167? What does that equal? What is that telling us? Total number of females, yep. And so then N2 would be total number of males. So the confidence interval for the difference in proportions, the 90% confidence interval, ranges from negative 0.237 to negative 0.09. Does that confidence interval include the value of 0? That's one way of saying that it's statistically different from 0. We're 90% confident that there is a difference in proportion of female students who are engineers versus male students who are engineers. That's using the formula, and then to go back to how we did it with the bootstrapping example, I'll walk us through that so we can see how these two are related. So with confidence intervals, we use bootstrap distribution. So which one would I pick for up here? We're going to do the same thing, a 90% confidence interval for a difference in proportions, but we're going to do it using the bootstrap method. What we just walked through was here's the formula for doing it, but then we can also do it by doing bootstrap. So you go up here for edit data, and it asks for count and sample size. When it asks for count, what is it asking for? Because that seems to come up as a confusing thing in this process. Start with sample size. You guys remember the two sample sizes?
I know 167.
Okay, that was women. The other sample size, 189.
Yeah, 189.
When it's asking for count, it doesn't want the percentage or the proportion. It just wants the raw count. So it would be 33, and then the same for males, it would be the raw count, which is 68. So that's how we set this up in Bootstrap. And so then what you notice is over here, here's our original sample, or our observed sample, and it shows that the difference in proportions is negative 0.16. And that's our point estimate. We want to find the confidence interval of it. We're going to use the original sample to generate 1,000 new samples to get 1,000 differences in proportions. Since we're using the original sample to generate this bootstrap distribution, it's going to be centered around the difference in proportions of the original sample. So like for the original sample, the difference in proportions was negative 0.16, and then for all the subsequent samples, it's going to be a difference in proportions. So like for this dot right there, this is the bootstrap sample, and it shows that for this one, the difference in proportions is negative 0.14. And you could go over every dot and see for that particular sample what was the calculated difference in proportions. And so then we want to know the 90% confidence interval for our point estimate of negative 0.16. So how would we find the middle 90% of values in this distribution?
You did two-tail?
Okay, so two-tail. What's the confidence interval for this? Okay, and let's see if that, we'll go back to, what you see is whether we do the formula version or the bootstrap version, it's going to give you the same confidence interval. It isn't like one's using the formula of the other. It's two very different processes. One is, yeah.
I have a question, because if you round up,
Mm-hmm.
is it, you have to have the exact same, or if it's like difference by like 0.001, is that a big deal?
Yeah, it's not a big deal. And in fact, it'll be different every time, because like the bootstrap sample is taking 1,000 random samples, but again, you take another 1,000 random samples and it's going to be slightly different. But that's why if you have a sample size that's large enough, then the differences are in the hundredths. The thing is that this is one way of calculating confidence intervals using a formula, and then the bootstrap sampling is pretending like you're taking 1,000 samples to find the distribution of the sampling differences in proportions. And so there are two very different ways of doing it, but this illustrates that both ways arrive at generally the same answer. So we did confidence intervals, and now we transition to hypothesis testing for differences in proportions. For hypothesis testing, we want the distribution of the differences in sample proportions, assuming the null hypothesis is true. So this is like doing a formal hypothesis test of our differences in proportions. So then we can compute the p-value using a standard normal curve and a standardized test statistic of the form z statistic equals test statistic minus null value over standard error. And so what we have is our test statistic is p hat 1 minus p hat 2 minus 0, and then over the standard error. That's why it's critical that you're able to look at a question and say, am I looking at a single proportion, or am I looking at a difference in proportion, or am I looking at a quantitative variable and looking at means or difference in means? A lot of it is just being able to read the question and know, okay, this is what I'm measuring. So we have the formula for the z statistic, and then it says now we need to estimate the value of the standard error. We have p1 hat and p2 hat, but then what is the standard error? We know that the standard error has this form, which is what we looked at, but what we talked about before is we don't know the population parameter for the proportions. You might say, well, why don't we just substitute in p1 hat and p2 hat, but that's not necessarily true for the hypothesis testing. And the difference is that if the null hypothesis is true, then p1 equals p2. We actually have more information than when we did the confidence interval. With the confidence interval, our best estimate was for p1 was p1 hat, and our best estimate for p2 was p2 hat. But if we're wanting to know the standard error when p1 equals p2, then the best way to estimate the common proportion is to combine the two samples into one big sample and find its pooled proportion. By assuming that p1 equals p2, we can have a better estimate of p1 and p2, and I'll walk through what that is. It's called pooled proportions, and it's probably a more complicated thing than it needs to be, but it's if the proportion of female engineers is equal to the proportion of male engineers, then you can just combine both subgroups, the female engineers and the male engineers, the sample proportion of all engineering majors across both groups. So it's like taking the variable, what proportion of all students are engineers? Then you can walk through p hat, which will be our best estimate, will be a value between p1 hat and p2 hat. Instead of using the individual proportions of female engineers and male engineers, it just says, what's the overall proportion of engineers? Because we know that when the null hypothesis is true, p1 hat has to equal p2 hat. So by substituting p1 and p2 with p hat, we get our final formula. Here's the standard error formula that we have. We want to find our best estimate for p1 hat and p2 hat when the null hypothesis is true. We substitute p1 and p2 with p hat, and if you walk it through, this is the most concise formula. With the standard error, this is for confidence intervals. We have our original formula of what standard error is, and when we did this, we said we don't know what the population proportion of p1 is or of p2, so our best estimate is p1 hat and p2 hat. And that's because that's all the information we have, and our best estimate is the sample proportion that we calculated. But the difference then when we're doing hypothesis tests is we have a slight bit more information so we can make a better estimate. P1, that's what you need to measure the standard error, but we don't know the population parameter.
Okay.
So P1 is the population parameter. We don't know it, so what we're going to use is our best estimate of the population parameter, and that would be our sample proportion. So our sample proportion is our best estimate. It's not, P1 hat doesn't equal P1, but it's a close estimate.
Okay.
And that's why it'll have that little squiggly over the equal sign. So with confidence interval with proportions, we take our best estimate. So it changes slightly though when we're doing hypothesis tests, in that with the hypothesis test, in order to make our best estimate of what P1 and P2 are, we have a slight bit more of information, and the slight bit more of information we have is that P1 equals P2. And so when we have that piece of information, we can actually make a better estimate for what P1 and P2 would be. We know that the proportion of engineers is going to be somewhere in between what the proportion of female engineers is and what the proportion of male engineers is. The overall proportion of engineers is going to be some number in between that. And so that's why we say P hat will be a value between P1 hat and P2 hat. And the way that you calculate it is this. And it's basically saying what's the total number of females times the proportion of female engineers plus total number of males times the proportion of male engineers, and then take the two sample sizes, add them together. And this is actually a value that you would already have. P hat is looking at the variable that says, are you an engineer? And what proportion of people said, yes, I'm an engineer, independent of male or female. This is a complicated way to get to our best estimate for P1 and P2 in the standard error formula. Once you've decided on what's your best estimate, you can make the switches, and then this is what the final formula comes out to be. We walk through the grid for hypothesis testing. This is, again, the same equation that we use, but then the challenge is remembering what is our test statistic, what is the null value, and what is the appropriate standard error formula to put in. If you take all those things in, here's our test statistic. We're looking at differences of proportions. Our null value is saying that there is no difference, so that the difference in proportions would be 0. And then this is our equation for standard error. The reason why there's, in a sense, 4 different days of covering this is because each one is slightly different. So when you're looking at single proportions, you can make certain assumptions. When you're looking at differences in proportions, it's going to look slightly different. When you're looking at single means, it's going to look a certain way, and then differences in means. To sort of break it up.
Is this still Z statistics? It's just with the numbers?
So this is going to give you, the Z statistic is the standardized test statistic. It's basically taking our test statistic and putting it into a standardized form, sort of like how we do the SAT and ACTs. Ultimately, what we're interested in is the p-value, and that's the area in the tails beyond the value for Z in the standard normal distribution. This formula is going to give you a number, and that's going to be the Z statistic for your test statistic. That's similar to what we were saying, like Z-score. It's like how many standard errors from the null value is this test statistic. And we'll walk through a specific example. If we do gender and engineering, are females less likely to be engineering majors, is our question. Pulling the formula from the previous page, the Z value is going to be calculated using this formula, and our p hat is calculated from this, looking at the sample proportion of female engineers and proportion of male engineers from our observed sample. So p hat, that's how we calculate it out, would be 0.284. What is 0.2 in this equation?
That's the limit.
Yeah, the proportion of female engineers. 0.36 is the proportion of male engineers, and then the null value is 0. Once you know which formula is the appropriate formula, then it's just a matter of pulling the information into that formula. But honestly, like when I think about using formulas, they're not particularly helpful if you don't know what's going on behind them. And that's where, when we did bootstrap sampling and the randomization, let you know more intuitively what you're measuring. You're measuring what would be the sampling distribution if the null hypothesis was true. And then this is doing it in a formulaic way. So we get a Z-score of negative 3.33. So can someone give, when you do all this and you get the value of negative 3.33, what is that telling us? The standard normal distribution. Yeah. Okay. How far it? What's it? That's fine. This is,
the mean difference in proportion.
So how far your test statistic, which from the null hypothesis. It's a Z-score for your test statistic. Chris, if the Z value is negative 3.33, where would that fall in the distribution? Within the 95% range, or?
The outside, right?
Yeah. You can kind of go back to the, plus or minus 2 standard deviations from the null value. That's the number 2, negative 2 and 2, and this is negative 3, so it's going to be way out here. But it's important to sort of, in the midst of walking through these formulas, to say, okay, Z is my standardized test statistic. Taking my observed sample statistic and standardizing it so that I can see where it fits on the distribution. And then I'm going to walk through and do it in StatKey where we did randomization. So with confidence intervals, we do bootstrapping, and with hypothesis tests, we do randomization sampling. So if we do that, we go here, which icon would we click on? So we're doing now hypothesis testing. So which one would we use? We're going to go and edit our data. The sample size, Tim, is what for N1 and N2?
It's 160.
167. And then the sample size for men, 189. And it's important when you're putting these in to know what your sample statistic is. Because like if you're doing men minus women, then you need to put all the men information in first in the top one and all the female information in the second one. So for hypothesis testing, you use randomization. And so then the count for the actual raw number is 33, and the raw number for males is 68. What this is doing, to remind you, is that with randomization, sampling distribution, it's saying what would the sampling distribution look like if the null hypothesis was true. Here's the null hypothesis that P1 equals P2, and it's going to generate 1,000 samples of what the difference in proportions would look like if P1 equaled P2. So then we do 1,000. This sampling distribution is going to be centered at the null hypothesis. It's going to give you a sampling distribution where the null is true, and it's saying that P1 equals P2, so P1 minus P2 is going to equal 0. This is what our sampling distribution would look like if we were in a world where there was no difference between female engineers and male engineers. And so this is the conditions under which the null hypothesis was true. And so then we take our original sample and we say, where does that observed sample statistic fit on the distribution of this randomization distribution? So how would we do that? So we want to know how many values are as extreme as our observed sample statistic. So these are two different ways of doing it. The z-score is sort of the standardized test statistic, but this is our way of doing it through simulations, replicating the experiment through simulation. Our observed sample statistic is negative 0.16, and we want to know what proportion of values are as extreme as negative 0.16. So we enter in what our observed sample statistic is. The proportion of values are as extreme as negative 0.16 is 0.000. I mean, because what this is the unstandardized test statistic, which is negative 0.16. And then the standardized test statistic was negative 3.3. And so what the standardized lets you know is if you see a standardized test statistic of negative 3.3, you know, wow, that's way off the charts. That's more than 3 standard deviations away from the mean. When it's unstandardized and you just have a value of negative 0.16, you can't intuitively tell, is that a big standard error or a small standard error? You don't know what to compare it with. But you can see from the p-value that, wow, it is very rare to get a difference in proportions as extreme as negative 0.16 in this case. But the reason why you do the standardized is so that you can know very quickly, oh yeah, negative 3.3 is going to be way more than 2 standard deviations away. Either way will give you the same outcome. And so what would be the formal decision with this hypothesis test? So we have a p-value of 0.000, effectively 0. What would be our decision with this hypothesis test? Reject the null hypothesis, yeah. And we interpret that the difference in proportion of female engineers is significantly less than the proportion of male engineers. It would be very rare for us to get a sample statistic of negative 0.16 if there was no difference between male engineers and female engineers. We did bootstrapping and randomization in the first section of the class. We did hypothesis testing and confidence intervals. And so The second section is looking at using the standard normal curve to calculate confidence interval and do hypothesis testing. But it's important to know both ways of doing it and then also how they're related. So even in the assignments, I think a lot of times it's going to come up. Do it using the bootstrap or randomization method, and then also calculate using the formulas for the standard normal curve. They're just coming at it from different directions. Just having the formulas will drive you crazy, and there's a lot of formulas. You'll get lost very quickly because you'll be like, I have no idea what values are supposed to go into what formulas. And so it's more being able to pull back and have a framework. What type of variable am I looking at? Is it a categorical or quantitative? And then what's my test statistic that I'm measuring? Is it a single proportion or is it a difference in proportion? You know, if you have a big framework and then you can answer some of those key questions, you can hone in on the right process. And that's what I've tried to do. Like, if we're doing confidence interval, you use bootstrap sampling. If you're doing hypothesis tests, you do randomization sampling. The only way to get it solidified in your mind is just by doing examples and testing yourself to say, okay, what is this one asking about? And then checking to see. The good thing by having two different ways of arriving at the answer, you can check yourself if you're doing it correctly. Because if the two processes don't match up, then you know, okay, I messed up somewhere. By taking this approach, the hope is to see, here's what's going on, here's what we're measuring, but it still doesn't make it 100% easier. And also I'd say, stop me mid-process and say, okay, wait, I just got lost. Yeah. What is Z again? Because I have to do it. I mean, I had to like walk through in my mind, what's the difference between Z-score and Z-statistic, and getting it all oriented. Really, I'm trying to hone in on the key things that you need to know versus a lot of extra ancillary aspects. The last thing for this lecture, we'll look at just accuracy, and it pulls the two together. The accuracy of intervals, which is our confidence intervals, and p-values, which is what you do with randomization, depends on the number of simulations. So we did 1,000 simulations, but you can even become more accurate if you do 10,000 or 20,000. So more simulations gives you a more accurate number. And then the accuracy of intervals and p-values generated using formulas in the normal distribution depends on sample size. So the greater your sample size, the more accurate it'll be. If the distribution of the statistic is truly normal and you have generated many simulated randomizations, the p-value should be very close. Like what Chris was saying, is it okay if it's off by 1/100th or 1/1000th of a value? And as you amp up the simulations or amp up your sample size, it'll become indistinguishable. Well, any questions about the final project as you read through what was expected or what you guys will be doing?
So is there a amount of references we need?
No. You know, basically, I don't want you just pulling something out of your head and being like, I think it should be this. More so, find something that will ground, okay, one reference per hypothesis. So basically, you're going to have a hypothesis. I want it to be grounded in something that someone published that agrees with you. I think probably, I haven't set this, but by Friday, I'd want you to have a research question in the variables that you plan to work with, so that I can help coach you in that process.
Will it be from the sheet you gave us, you pick from that?
That's probably the best.
Okay.
You can pull other ones, but sometimes like the question was only asked in 1 year, and so those are the ones that are asked every survey, and they're going to be on there, and they're pretty straightforward. So begin thinking about your research question and the variables, and then I can help you tweak it to make sure it works together.